Okay, so we saw a couple of videos where we saw how centrifugation helps in separation of biomolecules based on the uh, size of the biomolecules, also the mass of the biomolecules. The heavier molecules settle, and we are applying a force, and that force is the centrifugal force. And using that force, we separate the biomolecules. There is a supernatant, there is a pellet. So if your biomolecule is in the soluble fraction, then you must take the supernatant. If your biomolecule of interest is in the pellet, then you must take the pellet and then further proceed. Okay, so so this is the site actually from where I have taken the slides and all the information. I found this site very useful because everything is mentioned there, nothing is left out regarding centrifugation. I have only made a PowerPoint presentation using whatever information is there already. So we'll just go through the slide one after the other. Centrifugation definition: it is a device, it is a very important device which is used to separate components of a mixture. So before you proceed to ion exchange chromatography, or before you proceed for a gel electrophoresis, centrifugation is very, very important, because here it will separate the components from a mixture on the basis of size, density, viscosity of the medium, and the speed of the rotor. So we saw how a centrifuge looks also. There is a rotor, of course, and that rotor is holding your centrifuge tubes. That rotor is actually, you have identified the source, you have grown it into a medium. Now that source has produced biomolecules in the medium. Now you want to separate the biomolecule from the other medium components. So you are going to do centrifugation. It is commonly used in laboratories for the separation of biomolecules from a crude extract. So a crude extract is a mixture of many other unwanted things. In a centrifuge, the sample is kept in a rotor that is rotated about a fixed point. So when you fix the rotor, you have a screw to tight. You have to tighten the screw. So now your rotor is fixed to the shaft. There is a shaft, and your rotor is now fixed there, just like how you lock the mixer. So if you have used a mixer grinder at home, without fixing the mixer grinder, you cannot put it on. What will happen if you put it on? If you put it on the mixer grinder, the vessel, the pot of the mixer grinder, the pot may not be balanced. It will shake out, it will fall out. Okay, so just to avoid all of that, you also have to fix the rotor tightly. Now when you fix the rotor around to a particular point, now that it will just rotate around that point or around that fixed axis. Now this will result in a strong perpendicular force to the axis. There are different types of centrifuge that are used in the laboratories, in the R&D labs for separation of different molecules, but the principle is the same. The principle is sedimentation. We are using centrifugal force, we are sedimenting the biomolecules based on their size, on the density and the viscosity of the medium. The definition: it is a technique of separating. So first we saw the definition of the equipment itself. Now we are seeing the definition of the process of centrifugation. It is a technique of separating components where the centrifugal force, there are two types of forces, the centrifugal, centripetal. So centripetal is actually towards the center, centrifugal is away from the center. Acceleration causes the denser molecules to move towards the periphery, while the less dense particles move to the center. So now the tubes will go away from each other. Okay, so when you fix the tubes in the rotor, now what is going to happen is, because of the centrifugal force, the tubes are going to go away from the center, away from the axis. So the denser molecules will move towards the periphery, while the less dense particles will move towards the center. If there is any issue with the internet network, please call me. Okay, if at all I am inaudible in between, please call me so that I'll know. The process of centrifugation relies on the perpendicular force created when a sample is rotated about a fixed point. So this is something like I forgot the name of it. There's this. Okay, when I remember, I'll let you know. The rate of centrifugation is dependent on the size and the density of the particles present in the solution. So there is something which we there's a term that we use which is called as relative centrifugal force, or which is RCF. Now, what is RCF? It is measure of the strength of rotors of different types and sizes. So we are going to see that there are different rotors. So look at the size of the rotors. Look at the holder size. So this will hold a larger tube as compared to the second one. So the first one, the second one, the third one, and the fourth one. Do you see that the capacity is different? The holding capacity is different. The size of those holes or the holders are different there. So it's the relative centrifugal force is the measure of the strength of rotors of different types and sizes. The force exerted on the contents of the rotor as a result of the rotation. So RCF, or centrifugal force, is a force that is exerted on the contents of the rotor as a result of the rotation. So whatever content you are going to keep in there, the test tubes, not the test tubes, the centrifuge tubes, they are the special tubes. They are not glass tubes. They are made up of durable matter, because if it has to rotate at such a high speed, it should not deform, it should not crack, it should be able to sustain that force. So that kind of material is very close to plastic, but it is a high quality material, so it can sustain that force. And the RCF is the force exerted on that centrifuge tube, and the content inside, the content is going to be your crude extract or anything that you want to uh, separate. Your biomolecule is there inside and in that particular mixture, and you want to separate that. So that is going to be your content. Now, RCF is a perpendicular force acting on the sample that is always relative to the gravity of the earth. So we are actually exploiting the property of gravity of earth here, so gravitational force. So anything that you're going to, if you just keep a sand, you add sand to the water and you just keep it, allow it to stand on the table, you will see that because now the sand particles are larger, the sand particles will settle down. But also you must remember that, okay, the density is higher, they have a mass and they are going to settle down, but there is gravitational force of earth also which is acting on the sand particles. It is moving, it is pulling them downwards. Okay, so here also it's a RCF is a perpendicular force acting on the sample. Now your content is the medium which is having a lot of crude extract, different types of biomolecules of your interest, not of your interest, of different mass, of different size, of different density. So there is this gravitational force of earth which is also acting on them. Okay, it'll act differently. So it is a perpendicular force acting on the sample that is always relative to the gravitational force or gravity of the earth. The RCF of the different centrifuge can be used for the comparison of rotors, allowing the selection of the best centrifuge for a particular function. You will have different rotors, and different rotors have a limitation. So if you want to spin a certain rotor at a certain speed, you cannot use all of them, because these rotors are designed for different RCFs. Okay, so when you change the rotor, you'll also have to make sure that that particular RCF is being used for that particular rotor. Now, okay, centrifuge rotors. So these are the centrifuge rotors. The rotors in centrifuges are motor devices that house the tubes in with the sample. So here you are going to insert the tubes, and there are always even number of holders. So in this case, you will see there are 6 holders. In this, maybe there will be 10 holders. In this, there may be 4 holders. And again, here also 6 holders. So you'll always see that there are even number of holders, because I told you, if I insert the tube in, say, in this holder, if I insert a tube there, then I will have to insert another tube exactly opposite. So exactly in front of it. So this is the holder. So I will have to balance them. So if this, after I pour the crude extract in the centrifuge tube, and I have to first weigh it. Okay, if the weight of that tube is about 25 gram, then I have to take another tube, fill water into it, and then counterbalance it by counterbalance the rotor by keeping the tube containing water in this holder. Okay, so if you have 50 ml of medium, so you can divide that medium into half, and you can take two centrifuge tubes. But suppose if you do not have that much of crude extract to separate, you are just working on 20 to 25 ml, you do not have so much of medium to use as a balance, okay, then you can take water. But if you are working on a larger crude extract, then you can divide it into 2 tubes and then you can keep both the tubes, but both the tubes should weigh equal, not unequal. So like if one tube is 30 gram and if the second tube is 25, and if you keep 30 here and if you keep 25 here, the rotor is not balanced. The rotor is going to shake. The centrifuge has a sensor. If there is a sensor and if the rotor is unbalanced, the centrifuge will stop. Okay, this is like a modern updated kind of a version of the centrifuge, but previously there were no rotors and it would damage the centrifuge because you are actually using a high rotation there, and if it is unbalanced, then definitely it will break off. It may lead to an accident also. These rotors will hold the sample and the angle at which it holds is 45 degree in with respect to the axis, central axis. So this is the central axis. If you look at the center of each rotor, you will see that there is a place to here. See, look at this. Every rotor has a place, and then there is a shaft below, and that you have to lift the rotor and you have to fix it inside the shaft and you have to tighten the screw. So now your rotor is tight, and the sample tubes are at 45 degrees with respect to the axis of the rotor. Now the particles strike the opposite side of the tube where the particles finally slide down and are collected at the bottom because it is an angular, there's an angle. So now the rotor is going to move this angle of 45 degree. The tubes are not going to move because this is a solid rotor. Once you're fixing the tube inside, the tubes will not move, but your content is going to spin. Now that RCF that you are going to apply on the rotor will also be acting on the particles inside, on the biomolecules inside, and the heavier particles or the denser particles will finally slide to the periphery. They will be collected at the bottom, and the lighter or the denser ones will remain in the will move upwards. Okay, these are faster than other types of rotors as the path length of the tube increases. However, as the direction of the force is different from the position of the tube, some particles might remain at the sides of the tubes. So in this case, you'll have to do a trial and error method. So it's like if your biomolecule is not going to settle or sediment at a certain speed, then you will have to see, you have to check the sedimentation at a higher rotation. So what if you increase the RCF? Okay, what if you increase the RCF? Then probably it might settle down properly. Then the pellet will be tight bound. Otherwise, sometimes with insufficient or incorrect RCF that you apply on your crude extract, and if you spin at that particular rotation, sometimes the molecules don't sediment. They are loose. They will be still there, half down, half somewhere in the suspension, in the supernatant. You don't want that. So in that case, you can try, you can then you can fix after doing some certain trials, then you can fix. There are this type of rotor. Now that you saw is fixed angle rotor. You will see here that your tubes are not moving. Your tubes are going to be in at a degree at an angle of 45, but then this is a swinging bucket rotor. So I actually would like to show. So this is how you open the lid. This is actually the tight. So this is the central axis. The maximum load is also given. So the sample should not exceed beyond 600 grams, and the speed is 5,850 rotations per minute. Maximum speed.
And the video is not visible.
Pardon? You're
The
not able.
video is not visible.
Why? Okay. Is it visible now? Yes.
No, ma'am.
Now?
I'm not visible.
Okay. Sorry. Yeah. So you can see that there's a lid, and you'll see that there's some sort of a holder. That is not a holder actually, that's a holder cum screw, which will be connected to the shaft inside, to that axis inside. Yeah, so you see maximum load is 600 grams, not beyond that. Your sample shouldn't be like 700 grams or something. So these are the swinging buckets. Whatever he's showing, it's a swinging bucket type of rotor. Okay, so that's how swinging bucket, and this is like, these are very updated. There's a lot of updation in these equipments. Okay, so you will see sometimes the swinging bucket can look like the first one. So this is also a swinging bucket. This also is a swinging bucket. We just saw something similar to this. So depending upon how much is the holding capacity, if you are going to use it on larger volumes, you will use a larger container which can hold more sample. So swinging bucket rotors will hold the tubes at an angle of 90 degree. Can you see the screen now? Yes, can you see the screen?
Yes, ma'am.
Okay. So initially when we saw the first previous rotor, it was 45, this is 90. And the tubes are suspended in the racks that allow the tubes to be moved enough to acquire the horizontal position. So when this is like, you can see now this steel container, actually, this is just vertical or to the surface. Okay, now once I apply the speed to it, once the thing starts rotating, the position will become like this. So the tubes are going to be like this. All of the tubes will be like this. Okay, so that is they come at an angle of 90 degrees. So that's what is a swinging bucket. In this type of rotors, the particles are present along the direction or the path of the force that allows the particles to be moved away from the rotor towards the bottom of the tubes. So now this is your central axis. So away, centrifugal force, you're applying the centrifugal force. So the particles now will be settled. They'll go away. Okay, they will move away from the rotor. So they are going to move away from the rotor and they are going to settle at the bottom of the tubes here. Since the tubes remain horizontal, the supernatant remains as a flat surface, allowing the deposited particles to settle or to be separated from the supernatant. So now in this, you are going to get a clear cut pellet and a clear supernatant because of the tendency of the particles to move away from the rotor. Now then there is the third type, which is, so we are looking at the types of the rotors. So this is the vertical rotor. The first one was the fixed, the second was the swinging bucket. Now this is the vertical rotor, and it provides the shortest path length, the fastest runtime, and the highest resolution of all the rotors. Amongst all the rotors that we are going to see, vertical rotors are going to provide the fastest and the highest resolution. Now here the tubes are going to remain vertical during the operation of the centrifuge. In the initial, the angle was 45, the second the angle becomes 90. Here the tubes are going to remain vertical. The yield of the rotor is not as ideal as the position of the tube doesn't align with the direction of the centrifugal force. So here, since the tube does not move or it's not in the alignment as of the centrifugal force, the yield may not be great, but the resolution is good. Whatever resolution, whatever separation you are getting will be very pure and good quality separation, but the yield is not good. The quantity that you may get may not be good, but the quality of the resolution is very good. As a result, instead of settling down, the particles tend to spread towards the outer wall of the tube. So if you have this centrifuge tube like that, okay, this is the centrifuge tube, and then if your material is say green, I will just use the green color. So you will see that it'll all settle like this. Okay, rather than settling here, it will settle on the wall. These are commonly used in isopicnic or and density gradient centrifugation. We're also going to see the types in the next slide. Now, they were the types of, yeah, they were the 3 different types of rotors. Please put off your mic, everyone, okay? Because if you're benchtop centrifuge, continuous flow centrifuge, gas centrifuge, hematocrit centrifuge, high-speed centrifuge, low-speed centrifuge, microcentrifuge, refrigerated centrifuges, ultracentrifuges, and vacuum centrifuge, or they are also called as concentrators. So we are going to see briefly all these 10 types of centrifuge. This is the benchtop centrifuge, which is very handy, very convenient to use. It is kept on the bench, okay, on the working table. It can be kept on the working table, so it makes it doesn't require any floor space. That is another advantage, because in the labs there is a limitation to the space that you have in a working lab, and you have so many other equipments to keep. So this is designed especially for the table, and there is a motor inside, electric motor, and the tubes are rotated about a fixed axis. The principle is going to be the same. There is always going to be a fixed axis in all the centrifuges, resulting in the force which is perpendicular to the tubes. Because they are very compact, they are useful in smaller laboratories in smaller places. So this is sheer out of necessity, that how do we want a centrifuge in the lab, but the space is not so great. So what do we do? So we can go for a benchtop centrifuge, and different variations are also there in this benchtop centrifuge. And as I said, there are so many other companies. They will have different models, so you have a lot of choice depending upon what is the capacity to buy. So this belongs to Thermo Fisher company. This is from a Thermo Fisher company. A benchtop centrifuge has a rotor with racks for the sample tubes and a lid that closes the working unit of the centrifuge. So there is a lid. So this is your lid. It is not an open centrifuge. Mostly all the centrifuges have a lid these days. It's because to avoid the accident. It is also because you do not want any other contamination to fall in. It is also because when it moves, it makes a lot of sound. So that containing, when you close the lid, it is less of a disturbance. Okay. Also because you do a lot of centrifugation at lower temperatures. So if you're doing a refrigerated or a cooling if it is a cooling centrifuge, if your crude extract is very sensitive to temperature change, so you will have to maintain a low temperature. How will you maintain? Then you can also set a temperature in the centrifuge. Okay. So if you want to set a temperature, say at 4°, then this, when you close the unit, then that inside compartment is now cooled at 4°. So if you leave it open, then the outer air also will warm it up. So now centrifuges do not work unless and until you close the lid. If you leave the lid open and if you press on the start button, you get a command on the screen, lid open. So unless and until you do not shut the lid, the centrifuge will not work. Then there is continuous flow. The name itself suggests what it is. It is a centrifuge which is used to used for larger volumes. Okay. And so there is a continuous supply of the extract or the medium or whatever you're working with. There is a continuous supply. This is like a supply chain which is being made, and there is a constant pouring. The centrifuge is constantly working, and then you always get some stuff isolated or separated. So large volumes are used. Okay, they do not affect the sedimentation rate, which is very important, because the principle of centrifugation is working on the sedimentation rate. It allows the separation of large volumes at high centrifugal force, so thus removing the tedious part of emptying and filling the tubes with each cycle. So if you know that pellet is the important part for you, then supernatant will always be removed. It will be always separated. They have a shorter path length, which facilitates the process of pelleting out the solid part out of the supernatant, thus maintaining the speed of the process. So the speed is always maintained. You have to just set it once. There is a supply, there is a removing facility also. So you do not always have to set a temperature, set the time, and after 10 minutes, keep on coming, opening the lid, removing the tube, separating manually, again refilling it. Sometimes you're working with volumes like 100 liters. If you're using 100 liters of your crude extract, and if you want to isolate your biomolecule from there, imagine how many times you'll have to do this. every time come, balance the tube, put it inside, set the centrifuge, again take it out, remove the supernatant, refill it, keep it. So this is like a tedious process, a waste of time. So if in larger industries, in bigger industries, they know that they have a batch which is of say 100 liters, so they can use this. They can use a continuous flow centrifuge. They also have larger capacity, so time is saved because you don't have to load and unload the sample all the time like what you do in the traditional centrifuges. In R&D, in the research laboratories, mostly we are optimizing conditions, we are working on smaller samples, so continuous flow centrifuge is not required there. Something like a benchtop or something like some more other types of centrifuge we are going to see, that is also fine for us because we are working on volumes like 500 ml, 1 liter, at the max 10 liters. We don't go beyond that in the research laboratories. But when you transfer your technology from a research lab to an industry, then you are going to work on larger volumes. So in those cases, you are going to use a continuous flow centrifuge. And in each container, okay, in each holder, you can also put up to 1 liter of sample. And you can set them at the time can be 4 hours or even less, depending upon the molecule that you are separating. There is gas centrifuge also. It is used to explicitly used to separate the gases based on their isotope. So this is probably something which is used in nuclear, not in biological laboratories, more like chemical laboratories, more like places where they're working on molecules, atoms, and which are heavy metals or heavy, they are not light metals. Okay, so mostly there. So basically, you're going to use it to separate the gases. Okay. Then there is hematocrit. Again, this is hematocrit is heme is blood. So obviously it's used in immunology or immunological labs or research laboratories which are working on immunology. Okay. So hematocrit centrifuge is basically you have this hematocrit kits which can determine the proportion of red blood cells in the blood. Okay, so this is a very sensitive, can be used for smaller volumes. Of course, you're working on blood, so you're not going to have thousands of liters of blood. You are going to take the sample of the patient, and that will hardly be somewhere around 10 ml. So these are small, these are specialized centrifuges, and they are used to determination of volume fraction of erythrocytes, that is RBCs. So if you want to determine the proportion of red blood cells in a given blood sample, then this is the best centrifuge, because again, RBCs will have a certain density and they will sediment at a certain rotation. So if you just enter all of those details here, what is the specific rotation at which the RBCs settle, you set everything and you will only pellet out the RBCs. So this is a specialized centrifuge, and this centrifuge provides the values, okay, the values of hematocrit values that can be used for testing in biochemistry, immunity, blood test, and other general clinical tests. So mostly you'll find it probably in the pathological lab also. Hematocrit centrifuges may be used to help diagnose blood loss and all the other things which are related to immunology or medical or clinical tests. So it attains a speed of 11,000 RPM, okay, and the resolution, the separation is quite good because it's a specialized instrument here. This is also commonly seen in the research laboratories, which is known as a high-speed centrifuge. So benchtop and high-speed centrifuges are there in the research laboratories. So because sometimes if you are working again with not much larger volumes, but still considerably larger volumes, this is a good high-speed centrifuge. And it is kept on the floor, so it requires a certain dedicated area where it is kept. And the name, as the name suggests, this is a centrifuge that can be operated at a larger speed. Mostly there is a separate room, a small space which is away from all the other equipments which has been given to this centrifuge, because now the speed here can move, can go up from 15,000 to 30,000 rotation per minute. Okay. The high-speed centrifuge is commonly used in more sophisticated laboratories with biochemical application and requires a high speed of operations. Again, the lab, how much money can the lab spend to buy, because these are expensive, the maintenance and all that costs a lot. so sophisticated laboratories where they're working on very specialized things and where they need high speed to separate the biomolecule or any other component they are working on. They are provided with a system of for controlling the speed and temperature of the process. So because this is a constant rotation of the rotor that is happening, so rotation per minute is actually counted. So how many? 15,000 rotation per minute. So can you imagine that that particular rotor is going to move 15,000 times in a minute or 30,000 times in a minute? You're going to use that for 10 minutes or you're going to use it for 1 hour, depends upon the biomolecule. So if it is moving at such a high speed, then it is also going to generate heat. Okay, so if it becomes hot, then all the biomolecule or the sample that you have kept inside may also be affected because of the heat. So to avoid that, there is a temperature controller also. So that's why you set the temperature at 4 degrees, and then you must have a temperature controller. You must also have a speed controller in that. That's because just to avoid any mishap in that case. And also your the biomolecules or the other components that you are working on are very sensitive to speed. So the speed should be constant there. The high-speed centrifuges come with different adapters to accommodate the sample tubes of various sizes and volumes. So you will have different types of rotors, and different types of rotors can hold different capacity of liquids. So if you have a big rotor somewhere around, you can also use one container or one bottle of centrifuge, and you can use 1 liter of your medium. You can pour 1 liter of medium in that one container, in that one big bottle. But if you have only 25 ml and 30 ml, then you'll have to change the rotor. Okay, so if you change the rotor, you will be using it for smaller volumes. All the types of rotors can be used. So which are the 3 types of rotors that we saw? The first one was the fixed angle, the second one was swinging bucket, and the third one was vertical rotor. So all the 3 types of rotors can fit in this particular high speed centrifuge. Then there are low speed centrifuges, which are again used in laboratories for routine normal separation, not very specific, but they also occupy a small space in the laboratory. They are also something like benchtop centrifuges. Okay, and then the maximum speed you see is only 4,000 to 5,000, and they're very commonly used. Mostly every lab has this centrifuge, and usually operated under room temperature. If you do not have any specific condition that you only want to operate it at low temperature, and because your protein or other biomolecule or DNA, whatever you are pelleting out, is very sensitive to temperature, then you wouldn't use this. But if it's okay, if for your biomolecule, if it is okay to be spun under room temperature, there is no control of speed or temperature, then that's fine. It's just only mere separation. So you just want to separate out the heavy part from the suspension, then that this is what you should go for. You can also fix the swinging bucket and the fixed angle type of rotor. So only 2 type of rotors can fit in, not the vertical rotor that we saw. Easy and compact centrifuges, they are very useful and ideal for analysis of blood samples and other biological samples. Works on the same principle as all the other centrifuges, but the application is limited. So here only simpler separation can be attained, not very specific like we saw hematocrit. So we saw hematocrit because that requires somewhere around 11,000 to 15,000, the speed. Look at this, it is at 4,000 to 5,000. Hematocrit is also, it has the temperature parameter also there, but here you are not exploiting the temperature parameter. Here it is done under room temperature. So this is a different type used for different purpose. Now the 7th one is a microcentrifuge. These are, so the word micro means small. So is the centrifuge small? No, the centrifuge is not small, but the volume that you're working on can be also small. When you're working with molecular biology, on a project related to molecular biology where you're separating DNA, RNA, all of those things, they are not going to be in kilograms. Okay, they are going to be very, very tiny fractions of whatever suspension you have. So in that case, your preparation is not going to be much higher than say 2 microliter or 1 ml is the maximum that you can work in a molecular biology lab, not beyond that when you are extracting DNA and all that from a particular bacteria or from a plant source or from animal cells or whatever. So use for separation of samples with smaller volumes, and look at the range. It is from 0.5 to 2 microliters. Okay, it is that small, not even ml. It is microliter. So it is operated at a speed of 12,000 to 13,000 RPM, and they are used in molecular biology labs. They are also used for separation of cell organelles like nuclei and DNA, okay, via phenol extraction. So there are different extraction methods. So this is one of them. They're also termed as microfuge. So microcentrifuges are also termed as microfuge. Sample tubes are smaller in size when compared to the standard test tubes used in larger centrifuges. So if you're working on proteins, microfuge may not be of your use, because proteins are, you're going to scale up the production, you're going to separate them, the volumes are going to be much larger as compared to the DNA. But if you're working on cell organelles, if you're working on molecular biology, so microfuge is a must. Some microfuges come with adapters that facilitate the use of larger tubes also. So you can, so these days it is all about being more open to changes. So you don't have to always have one small rotor. So that becomes very specific. Also, because if a lab is investing so much of money into buying this particular equipment, then they may also want that they can use it for different purposes. So if a lab is working on molecular biology as well as some protein biochemistry projects, then they would want that, let us keep the outer body of the same, but can we have different rotors? Then if we are working on smaller samples, then we change the rotor, we put a small rotor. If we are working on a protein or something else where we do not want smaller rotor, we want to work on smaller, larger volume, sorry, so we will change the rotor in that case. So even in molecular biology also, sometimes it might happen that some experiments you will have to do on some larger scales and you will have to separate. So in that case, then just buying a microfuge and only for one purpose is waste. Space constraint is there in the labs. So you can have different rotors for different volumes. So there are adapters that facilitate the use of larger tubes also along with the smaller ones. So microcentrifuges with temperature controls are available for the operation of temperature sensitive samples. Molecular biology also is very, very, it's, I would say it requires the temperature factor. It's very important that the temperature factor is there in molecular biology experiments. Otherwise, the DNA would degrade if you just leave it like that, or some experiments may not work. So temperature is important there. Again, as I said, if you're going to centrifuge at such a high speed, then because of the generation of heat, the biomolecules may degrade inside. Okay, they are very sensitive to that change. Then refrigerated centrifuges. Again, there is a temperature control ranging depending upon what you're working, how sensitive it is to the temperature. This ranges from -20 to 30 degrees. So you can change the temperature depending upon the biomolecule. A different variation of centrifuges is available that has the system of temperature control, which is essential for various processes requiring lower temperatures. And they have temperature control unit in addition to the rotors and racks for the sample tubes. So temperature control is very important. Now the RCF can go up to 6,000 G, okay, which is very, very ideal for separation of various biological molecules. So typically used for collecting substances that separate rapidly like yeast cells, chloroplasts, and erythrocytes. The chamber of refrigerated centrifuge is sealed off from the outside to meet the conditions of the operations. You will have to always close the lid. If you don't close the lid of the centrifuge, none of the centrifuges will work because you'll always get an error lid open. So just to isolate the entire internal system from the external system, the lid ensures that all the conditions inside will be kept as you have set them. You can set the conditions. You have all these buttons here. You can set the conditions. So if you close the lid, the system ensures that the particular run will run under whatever you have set, okay, in those conditions. Then there are ultracentrifuges. So they are extremely high speed centrifuges, and they are used to separate smaller molecules like ribosomes, proteins, and viruses. We are talking about microscopic molecules here, okay. These are extremely small, so the density also will be different. They are not very dense, okay. So in that case, it means that if the density is not very high, then you will have to rotate them under high speed. You'll have to subject them to a higher RPM or RCF. Okay, so in that case, such centrifuges are called as ultracentrifuges, which work at extremely high. So these are extremely high speed centrifuges. So very sophisticated, because the separation of molecules, um, you cannot separate those molecules. You cannot use a ribose, or you cannot use a microcentrifuge, or you cannot use a tabletop centrifuge or the normal high speed centrifuge to separate these particular biomolecules. This is the only centrifuge which will allow you to separate these biomolecules. So refrigeration system is also obviously there inbuilt, okay, because heat may damage these very sensitive biomolecules. The speed can go up to 150,000 RPM. So can you see the extremely high speed I mean by this? It is not 15,000, it is not 30,000, it is 150,000 RPM, very high. Preparative and analytical work both. So analytical is basically just preparing, using something for testing in the lab. Preparative is getting a higher yield. So for both of them, you can use them, this particular ultracentrifuge, for both the preparations. Separate molecules in large batches and in continuous flow systems. So you can also, so we saw the third type or second type, if you remember, the continuous flow system also can be actually done here in this kind, in this particular type. So it avoids a lot of loading and unloading and manual tedious jobs. So it'll be continuous and it'll be error free. In addition to separation, ultracentrifuges can also be used for the determination of properties of macromolecules like size, shape, and density. So you can study the biomolecule also. You can keep on varying the RPMs, and then at a particular RPM, if you get a good yield and a good resolution, then that becomes a character of that particular ribosome or a protein or a virus. So then you can specify that this particular virus was very well isolated at a better yield at this particular RPM. So you can do that kind of study also on the molecule. Then the next centrifuge is vacuum centrifuge concentrators. So far, whatever we saw, vacuum was not a factor or a parameter there. But here you will see that along with the centrifugal force, vacuum and heat is used to speed up the laboratory evaporation of the sample. So sometimes there are some components after certain processing, after the crude extract you might have to subject it to some other treatment depending upon again what you are working on. Now, after you do that sort of treatment, probably you are adding, say, some solvent to it or something. Now, you do not want that solvent to stay in the biomolecule. It was only used for separation. Okay, it was only used for the isolation. Now, how do you get rid of that particular solvent? It may be ethanol, it may be isopropyl alcohol, it may be any other solvent. So here you can use this kind of vacuum centrifuge where vacuum is applied and heat is also used to evaporate the unwanted components from the sample. So capable of processing a large number of samples, up to you can use up to 148 samples at a time. So you can put 148 samples in this particular centrifuge, and you can start the centrifuge, and you'll be able to evaporate the substances which are not wanted. So they are used in chemical and biological laboratories for the effective evaporation of solvents present in the sample. And when you remove those solvents, obviously you will concentrate your sample. Okay. Commonly used in high throughput laboratories for samples that might have a large number of solvents. Again, depends on what component you're working on. As I said, it may be possible that you will have to add solvent at certain step, and now removing that solvent becomes mandatory to proceed further. So then how will you remove that solvent? Because if you heat it just in the open air, or you just leave it open, because solvents evaporate also. If you're talking about alcohol, isopropyl alcohol and all those things, you know that at a certain temperature they evaporate. But they may evaporate, but at that temperature your biomolecule may degrade. So what are you achieving? You are achieving the evaporation of the sample, but at the same time the biomolecule also has lost its function or structure. So you don't want to do that. Now what will you use then? You are going to use a system where you have an enclosed system where the temperature is also maintained, so taking care of the biomolecule, but at the same time effective removal of the solvent is also happening, because you're applying vacuum to it. You're not using, just not exposing it to the atmosphere and doing a crude evaporation. You're doing it under specialized conditions. So it will definitely take care of the biomolecule that you're working. Okay. Now a rotary wave evaporator is used to remove the unnecessary solvents and eliminate solvent bumping. So yes, it's a very well-maintained condition inside, because if you do not take care of certain factors, the solvent may just jump out of the container. Okay. And if that jumps out of the container, obviously there is going to be a spillage inside the equipment, but along with your solvent, along with the solvent that will bump out, the biomolecules may also bump out, and that is not good. And at times you are using, so if it's a big lab, there are many students working, and many students have the same kind of sample, but the biomolecule is different. So some is working on, say, A, and others are working at in B and then C. So there are some students who are working in biomolecule A, B, and C. So they have some samples to be evaporated. Okay. Now this person has, say, 20 tubes, this has, say, 30 tubes, and this has, say, 40, and this has 50. So they all decide on a day, because it's a big equipment. Only for 20 samples, why do we run one equipment? So they all decide on a particular day, and they say that, okay, my samples will be ready on Monday. Let's start together. Let's start this particular centrifuge together. So we are using it in a proper way. So they all put their samples in. Now, if the sample bumps out from this particular tube of the preparation, it might contaminate the others. It might, spoil the equipment from inside. Some solvents are not so inert, it might damage. So just to avoid that, there is a rotary evaporator. You'll see all the setup here. There is a tube, there is a collector. So whatever evaporates is collected through the tube, and it is discarded, it is collected in a container, and you can throw that stuff later. You can dispose it properly, because it is solvent, it is chemical. You cannot throw them in the sink, otherwise you will be damaging the environment. Okay, so there is a proper disposal way in the laboratories where you can dispose the stuff. The centrifuge works by lowering the pressure. Yes, because when you play around with pressure, vacuum, and all those stuff, evaporation increases, which also decreases the boiling point. So evaporation will increase, and if you lower the pressure, the boiling point also will decrease. You do not want unwanted accidents in the lab. So these are all very specialized techniques. This causes the solvents to evaporate, and then it will concentrate the particle also. It will separate it. The resolution is quite good. Then types of centrifugation. So the first type we are going to see here is a analytical centrifugation. It is a separation method where the particles in a sample are prepared on the basis of their density and the centrifugal force they experience. It's a very robust method for the quantitative analysis of the macromolecules in the solution. Now, principle of analytical centrifugation is based on the principle that particles that are denser, they will always settle down faster. Similarly, the larger molecules will move quickly in the direction of the centrifugal force than the smaller ones. The smaller ones will probably remain in the upper area. Analytical centrifugation for the determination of the relative molecular mass of a macromolecule can be performed by a sedimentation velocity approach or sedimentation equilibrium methodology. So basically, when you want to study or you want to do a quantitative analysis of the macromolecule in the solution, you're going to use this approach. You're going to use the analytical centrifugation approach. Okay. Now, the sedimentation coefficient will depend on a lot of things. It will depend on the size, it will depend on the shape of the micromolecule with changing the experimental conditions. So the size and the shape of the macromolecule is also determined by the experimental conditions. So what if the experimental conditions are changed? So suppose what will happen if you have a biomolecule in an aqueous suspension, like a proper buffer system? Obviously the size and the shape of the macromolecule probably will be at the optimum best. Okay, but if the same macromolecule is subjected, say, to a solvent, okay, now there things might change. So when you change the experimental condition, then the sedimentation coefficient also may change. So you can use that sedimentation, the property of sedimentation as one of the characterization studies for that particular macromolecule. Now, three optical systems are available for the analytical ultracentrifuge: absorbance, interference, and fluorescence, that permit precise and selective observation of sedimentation in real time. Now, there are a lot of updations in this area, so you can now study it in real time, like what is happening right now. So based on that, also a lot of information is obtained on the particular biomolecule. So what is the absorbance, what is the interference, what is the fluorescence, is the biomolecule of your interest right now in the sedimented state, or is it still in the process of sedimentation? So are you getting more absorbance in the supernatant? Okay, while actually the centrifugation is still happening inside, you can actually there is a device inside which is going to measure the absorbance also. So is the pellet, what is the pellet absorbance, what is the absorbance of the supernatant? So every molecule, we studied in the spectrophotometer that every molecule is excited at a particular wavelength. Okay, so if you're working on ribosomes, if you're working on any other protein, it will have a particular wavelength at which it will resonate, it will get excited. So what is that absorbance? So if you're only separating, say, protein A, and protein A has a certain absorbance at a certain wavelength, you can, because of these techniques now, because it can absorb as the centrifugation is happening, you can keep on getting a data that the absorbance in the supernatant is right now very high at a particular wavelength. It means that the protein A is still in the supernatant. But as the absorbance starts decreasing of the supernatant, it can also be indicated now that the pellet is having the particular biomolecule A. So these are certain updations, these are certain developments that keep on happening in this area. Uses of analytical centrifugation. Analytical centrifugation can be used for determination of the purity of the biomolecules. It can also be used for the examination of changes in the molecular mass of supramolecular complexes. Besides, it allows the determination of the relative molecular mass of solutes in their native state. So you do not want to disturb or distort the biomolecule from its native state. So analytical centrifugation helps you. It can be used for the determination of the purity of the macromolecules in this case. There are different types of centrifugation, such as density gradient centrifugation. And in these further slides, there is a lot more about, say, sucrose. How do you use sucrose for doing a density gradient centrifugation? This we will see in the next class.